well, kind of clear when we do the graphing of sine and cosine and tangent length. But what we need for this section is just to know what's going on with this periodic business. And like I said, it's kind of what would you cut and paste and then constantly redo in order to get the whole thing. And that's what the period is. So sine and cosine, a period of 2 pi. Tangent are pi. And these predictable, repetitive behaviors help us model behavior in the real world. We're not going to jump into word problems at this point, but we want to see that repetitive behavior and how that'll help us calculate some of these. So a function y equals f of t is periodic if there is a positive number c such that f of t plus c equals f of t. What on earth are they saying? You start with your sine curve, and you realize that if you add 2 pi, you're going to be in the exact same place. So that would be our c for sine and cosine. You start with your tangent, and you add 1 pi to your x's, and you find out it lands in the exact same y value. So that's what they're saying here. For all values of t in the domain of f, the smallest such number c is called the period of the function. So for sine and cosine, 2 pi to get that repetitive behavior. For tangent, 1 pi. This behavior also helps us to train ourselves when we cannot and or should not use the calculator. You know, we're not supposed to use that calculator when we talk in radians, which frightens us when we get to the next one where they have us doing problems. But what we're going to do is this. We're going to visualize, okay, it's got this nice curve thing going here. And for cosine, if you want to see the whole thing, you have to go 2 pi. This is 0, this is 2 pi. You cut and paste that, boom. You have more of the graph. Cut and paste it again and again in both directions, and you have the full graph, and it goes on forever. For sine, it's the same thing. Obviously, it looks different from 0 to 2 pi, but if we cut and paste that, we'll have the full graph for the sine curve. And then tangent is different, because tangent is using both our y and our x, which we talked about yesterday when you're using coordinate geometry. Your x is now cosine, and your y value is now sine. So we're taking our sine over cosine to talk about tangent, opposite over adjacent. And that gives us from negative pi over 2 to 1 pi over 2. So you think, okay, if I'm at negative 1/2 pi, and I have to go to 1/2 pi, that's really just 1 pi for that distance, and that covers it. But here's the thing we want to notice. This y value is exactly the same as this y value, which is exactly the same as that one, which is exactly the same as that one. How much distance is between those green dots? 1 pi, because tangent repeats in terms of 1 pi. That's its period. Up here, we notice this. And we think, okay, well that's not the 2 pi thing that I'm looking at. Well, that's because it's not the same point on the curve. At this point, the curve is going up. So the only one that's going to match that is this one, because the curve is going up at that point. Over here, this is going down, so we want to get to the part of the curve where it's going down again. And now we see that 2 pi repetitive behavior. So the y values are going to be the same. So what does that mean? If somebody asks us to find the cosine of 4 pi minus the cosine of 2 pi, the answer is 0. Because at 4 pi and at 2 pi, we will be in the exact same y values. So if we subtract those, they're 0, because they're the same. So on the next page, we don't want to think, oh my gosh, look at these huge numbers, oh my. We want to think about the period of the function. So, wow, I don't know about you, but I'm not drawing 57,801 pi over 2. I'm going to do that. So there must be something about this that we're supposed to recognize. And that something comes from realizing that every 2 pi, this is going to repeat and start over. So we could grab a calculator and figure out what are we talking about here for how many rotations this is going to go. So if we take 57,801 and divide it by 2, we get that. 28,900 and a half. Yeah. Oh, does anybody else need one today? Couple people. And I'll talk you through that in just a second. All right. If we weren't going to use a calculator, we would basically do the same thing, except here's what we would do. We would say to ourselves, all that really matters is the remainder, because every 2 pi, this thing is going to do the same thing every time. So really what we would care about is this 1 digit right here, and we'd say, well, if this is, even if you wanted to do 801 divided by 2, you'd realize you're going to end up having a remainder of a half. And this is pi. So it doesn't matter that they're talking about 57,801 divided by 2 pi. It's still going to land at pi over 2. The remainder is what's important. So with or without a calculator, you just need to figure out, well, let's see, an even number doing the 2 would give me a 0, so I'm going to have a remainder of 1. So this is really about finding pi over 2. And that's what we have to do. We have to find the sign of pi over 2. Pi over 2. Put it in degrees in your head. What is it? 90 degrees. So think quadrantal. What do you want to do for 90 degrees? 0, 1. And remember that r is already 1. So if we're finding sine is going to be what? Y over r, 1 over 1. And we have it. So yes, huge numbers, but all we really care about is the remainder, because if it's even, that's bringing us right back to 2 pi. And then whatever we have left is what we're going to need for the angle. So let's look at B. That does not look like fun. 288.45 pi minus the cosine of 280.45 pi. How far apart are they? Well, wait a minute. If cosine always repeats at 2 pi, won't they be exactly the same thing? Yeah, because we've got 4 2 pi's. They're going to land in the same spot. So this is the same thing as that. So what's the answer? We can see that between the two, it's a difference of 8 pi. It repeats every 2 pi. It's going to land in the exact same spot for both of these. We're going to subtract and we're going to get 0. Oh my goodness. Look at that. Oh. There's a big part of this we don't need. What is it? Right there. How come? What's the period for tangent? 1 pi. This is blah, 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 pi. It's going to take this, it's going to twirl it around a whole lot, but where's it going to land? Right back here. Tangent of pi over 4. Tangent of pi over 4. Pi over 4. Think in degrees. Do you remember your sides? 45. 1, 1, square root of 2 in the triangle game. There we go. All right, so we need tangent. 1. Done. So if you see problems with lots and lots of digits in your homework, you should be thinking, okay, this is one of those trick things. I need to look for either 2 pi's or I need to look for 1 pi's for tangent. So as it says down here, at this point we should be able to use reference triangles and quadrantal angles to evaluate the trig functions for all integer multiples of 30 degrees or 45 degrees. And of course the radian counterpoints. That's much more important to us, the radians piece. So we have this nice little unit circle here, which remember means that the radius is 1. And like it says, this diagram is given so we can visualize all of the trigonometry that we're able to do, but we are not going to use this as we're working through the homework. So here's what we're going to do next. We're going to generate that unit circle. If you did it by yourself without me acting, you could probably do it in 2 minutes. And at first you're not going to believe you're capable of it, but I'm going to show you how to do it. And while I'm handing out these worksheets, you're going to need at least 2 highlighters / colors from that bag if you did not bring your own. And that will make this much, much easier. And the visual will definitely help you. And while I get mine loaded up on the computer here, on the back of this page, I want you to generate your 2 special right triangles, your 30, 60, 90, and your 45, 45, 90. Get all those sides on there, get your angles labeled, all that good stuff. Apologize, it's got to be kind of small to get that circle in there. All right, you got your 30, 60, 90 and your 45, 45, 90 generated on the back, right? So here's what we're going to do. We're going to break this into pieces that would be 30 degrees at a time, and then pieces that would be 45. So grab one of those colors, and the first thing we'll do is take one color and we'll go around, and anything that's going to be a part of that 30-degree piece as we go around, we'll get that color. So I'm going to put red here, because there's my starting place. And then I'm going to the first 30 degrees and putting red there. Now that's not another 30 degrees, that's the 45 marker. So I have to go up here to the next 30 degrees. So keep doing that all the way around the circle, marking those 30-degree pieces. Now we're going to go put those degrees in there. You can see there's a degree and a radian spot. So we'll go through and say, well, this is 0, this is 30, anything with my red up here, 60, 90, 120, 150, 180, 210, 240, 270, 300, 330, and 360. Now we're going to do it in radians. I'll make sure everybody's caught up to this point. 30 degrees is what in radians?
pi over 6.
Pi over 6. So what we have to do is go around, and every time we do one of these, we're going to add a pi over 6. So we've got 0 radians here. This will be pi over 6 radians. Actually, it looks like I'm supposed to write that as a fraction. There we go. But then I'd have 2 pi over 6. Wait a minute, that's going to reduce. Oh, 0 and 360. Let me put my 0 here too. 0 radians, 0 degrees. 0 or 360 are going to give us the same exact trig functions because of our period of 2 pi. Oh, I had it in the wrong spot. Thank you. I noticed that when I landed there and didn't have any space for it. All right, we did 1 pi over 6. This would be 2 pi over 6, but we wouldn't leave that, right? Because that'd be pi over 3. But still be thinking, I had 1 pi over 6, 2 pi over 6, 3 pi over 6, pi over 2, 4 pi over 6, 5 pi over 6, nothing we can do with that, 6 pi over 6, well that's 1 pi. 7 pi over 6. Nothing we can do with that. 8 pi over 6, we can. 9 pi over 6, definitely can. 10 pi over 6. This is so small. 11 pi over 6, there's no reducing that. 12 pi over 6, yeah, that's where I would have noticed my 2 pi was slot there. So that's by doing all of the 30-degree wedges. That took care of 30 and 60 degrees by doing that. So now the other color that we have is for the 45s. Anything that we could use as 45. So we're again going to start thinking from 0, that initial side. So I'm putting a little green here. But now my green is going to go to this wedge because that's a 45-degree wedge. So is this. So is this. And just go around and get those 45-degree wedges colored. .45 degrees. Let's go put the degrees on here. We already have 45 times 2 is 90, so then we'll have 135 plus 45 would give us 180. Plus 45 would give us what? 225. Plus 45 gives us 270. 270 plus 45. So we've got it in degrees. Now, degrees is not really what I was worried about. This is much more helpful to do the chunks as you're doing this in radians. So 45 degrees, what is that in radians? Pi over 4. So we've got 1 pi over 4. 2 pi over 4, shouldn't shock us that that's pi over 2. 3 pi over 4, nothing we can do about that, we're just going to use it. 4 pi over 4, that's 1 pi. 5 pi over 4, can't reduce it. 6 pi over 4 reduces to 3/2. 7 pi over 4, and then we're at 8 pi over 4, which is 2 pi. So we have all of that generated on there. Well, now we look at all those points and go, oh my gosh, we have to do all of that? Well, not really. Let's see what we need to do. If we can get first quadrant, we can get the rest of this just fine. So remember, x is cosine, and y is sine. So what we need to start with is we need the cosine of 30 degrees. Flip your paper over. Get me the cosine of 30 degrees. Square root of 3 over 2. Now get me the sine. Opposite over hypotenuse 1/2. Let's do the same thing for 45 degrees. Find the cosine. 1 over the square root of 2, but then rationalize the denominator. Square root of 2 over 2. What's the sine? Same thing. Square root of 2 over 2. That's really all we need. That and some knowledge about geometry and trigonometry. Because 30 degrees and 60 degrees are cofunctions. That means the sine and the cosine are going to flip. So this one will have 1/2 as its cosine and square root of 3 over 2 as its sine. Now we can come back and hit the quadrantals later, but we don't really need to do that either. You remember what happened with our special quadrantals? Things worked out really nice, right? What are the coordinates of this point? We're done. We have the cosine and sine of 90 degrees. Right here. Down at the bottom. So those aren't the issue. So how do we get all the rest of this stuff? By symmetry. We don't need to redo it all. Look at this one. We're going over this amount and up this amount. We're going back this amount and up this amount. The x's are going to stay the same, it's just one's going to be negative now. So this will be negative square root of 3 over 2, 1/2. Here's our pi over 6 and our 5 pi over 6. They're symmetric. You're reflecting over the y-axis. When you do that, the x changes to negative. Well, we can do that for all of those. The x becomes negative. Has to, it's a circle. It's symmetric. These points reflect over the y-axis, making the x negative. So, how could we get third quadrant? Make them both negative. Negative x's and now negative y's. One more quadrant to go. Quite honestly, I just start back at the beginning and say, hey, this is going to be reflected over the x-axis. I'm going to make the y's negative. That's what makes sense. Now, last thing to check would be, does this match what it's supposed to when I think of sine, cosine, and tangent and their signs? Positive, positive, and positive. Well, if cosine is positive and sine is positive, then tangent's automatically going to be positive. Positive, negative, negative. Okay, so my sine, which is my second position here, those are all supposed to be positive. They are. And all of my cosines will be negative. So yeah. When you do sine over cosine, you're going to get negatives. Plus, minus, minus. Minus, minus, plus. Sine is negative. That almost doesn't look like a negative. It looks like part of the fraction line. Cosine is negative, and negative divided by negative will give us a plus. Over here, minus, plus, minus. Sine, the y values are all negative. Cosines, all positives. And if you take the positive and divide it by the negative, you get a negative. So like I said, I took this slow, but once you get good at this and fast at it, then it's not much trouble at all to go ahead and fill out the unit circle. So the color coding helps a lot with getting those pieces so you can see 1 pi over 6, another pi over 6, another pi over 6, and keep working your way through it. Because some of the teachers, well, you've got me second semester, so I guess you don't have to worry about this. I don't do memorizing. I don't think you should memorize things because then you're going to forget. And they will actually have you memorize the unit circle. I don't do any memorizing of the unit circle. I think my way through it every time. And that's because thinking your way through it helps you with the more difficult trigonometry that you need to do later. Being able to recreate those 30, 60, 90, and 45, 45, 90 triangles, that's a skill that you just cannot devalue. It's huge. If you know that information, it'll help you out with a ton of tricks. But this is something we do need to get fast at. So we went through one of those together, and I'm going to give you another one. And it's something you should practice, is going through and doing this on your own over this weekend. Because the worksheet that I'm going to give you, in addition to what you have for homework, has you set a timer and try to find trig functions using that unit circle and trying to get faster and faster at that. Now, if you are a memorizer, I would recommend that you just memorize the values for pi over 6 and the values for pi over 4. That's not a hard thing to do. But then use symmetry to get the rest of them. And normally I would say, you know, I'm not about the speed thing, but it is one of those things where the problems are going to go much faster for you if you are able to do this quickly. So, raise your hand if you think you could recreate that on your own, start to finish. Okay. So, it's going to take a little bit of work for some, but we need to be able to do that. And then, the reason this assignment looks smaller is because, like I said, I'm going to give you the worksheet now to work on that unit circle stuff. Because our plate's pretty full for Monday and Tuesday. We're going to be reviewing for your test. And so what I'm going to do is, at least it didn't break. This sounded like normal. Dropping, that happens. So here's what I would do with this worksheet. Tonight, not now, because right now it's really fresh in your mind, but tonight at some point, fill out the unit circle and do those first two groups of 10 on the front, where it says, and I'll get them up to you, but it says give yourself 6 minutes. You know, give yourself 6 minutes to find these trig functions. So you set a timer. See if you can get them in that 6 minute zone. And then on Sunday afternoon, flip it over and challenge yourself to do it faster. Again, like I said, I'm typically about quality, not quantity, but there are several times when it needs to be like the back of your hand. Yes, I know this. You know, I know the tangent biology. And you're able to do that very quickly. So like I said, for me, tonight, I'd fill out the unit circle and I would do the 2 on the front, set the timer. Can I do this in 6 minutes? And find all these trig functions. And then on Sunday, come back to the back. And now the timer is set at 5 minutes, and then 4 minutes, and then 2 minutes, and then 1 minute. And see if you can do those a little bit faster each time that you get working with them. Because like I said, it just needs to be something that we can do very quickly. But that's what I have for you. And then this would be another one you could maybe use on Sunday to practice, get yourself back into them before you go to do the back side of that worksheet. But it's totally up to you. You know your time and you know what time you have to do this. And we'll go over any questions for Board 3 on Monday, and we'll do some reviewing, and then we'll do some more reviewing on Tuesday, and then we'll take a test on 4-1, 4-2, and 4-3 on Wednesday. I did have her make lots of extra copies of the unit circle. So if you're thinking you're gonna want more than one to practice over the weekend, I'll just put a pile of them on the black card. And you can grab another one. Never hurts, practice makes perfect.